Chapter 4 is the topic of networking. Of course, this is a very brief flyby of the topic, and our goals are going to be modest. The term networking is used broadly in our culture, and it refers to everything from social networks to specific communication technologies. A network is any group of people or things that are somewhat organized for the purpose of sharing data and information. We see networks of devices everywhere we go. Traffic signals, cell phone towers, modern gadgetry such as cook stoves, cars, mobile devices. Now, when we think about a kind of network, we should shift our thinking to the scale that fits that network. For example, in the context of you as a Rotary Club member, your network is the people and the scale of that level of people in your local Rotary Club. On the other hand, if you were studying the communication between the roots of various fungi, your scale of focus would be much smaller. Size and context are keys here. Given our focus of this course being computer networks, keep in mind that there are many different scales of interest. Your home network is a very different scale than the internet across the world. So for purposes of this class, let's keep our discussion at the human scale in a local business. Computer networking is a huge topic. For our purposes, we'll focus on some of the more common concepts and terms. First, let's define what a computer network is or does. It's the connected association of two or more computers for the purpose of exchanging information. One salient topic is describing the speed at which these connected devices exchange data. We refer to this rate of transfer as bandwidth. This term has very technical roots. For our purpose, let's discuss it and say that bandwidth describes the rate at which digital information is passed. Given the smallest unit of measure of the digital information is the bit, we often measure bandwidth in the number of bits that can be passed in a second, hence the term bits per second. In today's world, it's common to see millions of bits per second, megabits per second, to call it, or billions of bits per second, which is gigabits per second. Another term of interest is broadband. This refers to the capacity of a communication medium to carry information. But it refers to the capacity of some types of medium to carry more than one signal at a time. Over that signal wire that comes into your home for your cable TV, many channels can be sent simultaneously. Is your internet access to your home that you probably have some form of broadband service to that home. A digital subscriber line, or DSL, send multiple channels of information over a single phone line. Cable modems use the cable TV wire to send data channels. Today, there are many ways to get broadband at home. Fiber to the home, direct wireless, satellite service, name just a few. We also have terms that attempt to inform our understanding of the scope of the network services. Within the information network, a local area network, or LAN, refers to a relatively small grouping of computers, usually within the same building or campus. While there are some practical limits to these connection arrangements, they usually are distinguished by interconnecting network devices called routers. The role of routers is to separate networks. Wide area networks, or WANs, are also separated by routers, but usually require some third-party vendor to provide connection between the LANs. For example, I might use a Verizon wide area network to connect to two LANs in separate cities. The term enterprise network typically refers to all the computer networking services in an enterprise or company. These enterprise networks can be quite complex. The bottom line here is that as we scale up the capacity of a network, we start adding new communication devices to support that more complex configuration of computers. No matter how complex the networks, the fundamental job is still transferring data between computing devices to help people do their jobs. This simple drawing is intended to point out that network technologies are about connecting computers and other input-output devices like printers These kinds of logical diagrams certainly don't show how the connections are made, but are used to show the communication paths. One of the most popular networking technologies for interconnecting devices is called Ethernet. This technology has been around since the 1970s and is still being improved to support modern networks. You might find that the history of Ethernet is an interesting read, but for our purposes, let's just say that Ethernet refers to the physical connections and cables. That means that each device on the network would need to have an Ethernet network interface card, also called NIC, that connects the device to the network. We'll come back to a little more detail about Ethernet in a minute. And although there are many other networking and connecting devices in the marketplace, we'll limit our brief discussion to Ethernet. For those of you who are visual learners, this slide is included to help you understand enterprise networks. The scale of this model is within a single enterprise. The various functional LANs could be in the same building or someplace else in the world. Where the parts are located would determine whether we need just local area network technologies or wide area technologies. Notice that there is an interconnecting network called a backbone. Think of this as a kind of large traffic roundabout that lets any individual LAN talk to any other. There's some nice benefits to using this kind of architecture, as it provides for easy growth of the network, and it also provides for some fault isolation. For example, if the satellite of a LAN fails, it doesn't bring down the others. Notice the term file server associated with the mainframe module. Mainframes are highly powerful, specialized computers that do large amounts of processing in a very short time. File servers are handy that allow us to use other computers to store and share information. They are also a location where we can run shared applications. In our brief treatment of computer networks, it might be useful to consider some of the characteristics that make these shared resources so powerful. Over the next couple of slides, we'll talk about the three topics on this page. Of course, this once again is a bare introduction, but it'll help to give you some context in which to think about how networks work. Media is the term used to describe how information gets transported between devices. We tend to chunk media into two types: wired and wireless. Today, wired networks require that we pull some type of cable between each of the connected devices. Typically, a wire-based technology includes twisted pair, coax, and fiber optics. Wireless media uses air to transmit radio waves, so they don't require physical cables. Some form of wireless signals can go through walls, others can't. We spend a slide or two on this topic as well in a minute. Now, the term network protocol refers to special formatting used to package up information and transport it across some form of media. Think of a protocol as a special set of communication rules that help devices, in their communication to effectively talk to each other. These rules are embedded with the information in a transport device known as a packet. Another topic which the book refers to is network processing. This rather unfortunate term that describes how programs and other applications are dispersed across the network, but the next few slides will expand on this. In this slide, we are slightly expanding the idea of network media. Now, recall that I said we have two types of media, wired and wireless. Most of the wired networks today use one of three forms shown here. Twisted pair wire is a hand-me-down from the old telephone days. This unshielded twisted pair wire doesn't have the electromagnetic noise protection built into the wire bundle. The twisting of the wires allows for a form of noise protection that is typically good up to 300 feet, depending on the ambient electromagnetic noise in the environment. Literally all Ethernet cables you see in the office today are twisted pair. They have 4 pairs of wires, and Ethernet requires 2 of those wires. The other pairs can be used for a variety of other purposes. Now, coax cable has been around for a long time and is typically the cable used to bring cable TV to your home. Coax has a single data wire and is protected by a sheath of metal mesh used to shield the data from outside noise. It works well in noisy environments, but its cost and bulk have made it less desirable for LAN connections. Each type of cable has length and speed limitations that dictate their optimal use. Fiber optic cables support very high speeds and are immune to electromagnetic noise that affects the other wired technology. While they have superior performance characteristics, they tend to be expensive and relatively inflexible. The choice of wired media today is matched to the performance characteristic needed for the task. Wireless technologies use small radio transmitters to send data signals through the air. And while performance characteristics of wireless technology are rapidly increasing, they do have some environmental constraints that control their practical use, sometimes called mountains. The trade-off between wireless and wired networks has to do with their bandwidth, the cost of implementation, and the signal distance that's supported by them. A more technical aspect of networking has to do with how information is coded when being prepared for transport across the network. Now, we're all familiar with some sort of FedEx or UPS package and how they're coded for shipping. We put the item into a shipping container, and then we affix the relevant information to that package so that we route it to the right location. This is essentially the job of the network protocols we talked about. We chop information into manageable sizes and stuff them into enough packages to get all the information to the other end of the communication. Unlike UPS packages, we can only ship so much information in a single package. For example, common Ethernet packages only allow us to ship about 1,500 characters at a time. If we wanted to ship 15,000 characters, we would have to create 10 information packets to accomplish that job. The protocol typically used by Ethernet is called Transmission Control Protocol, Internet Protocol, or you've seen somewhere probably as TCP/IP for short. Transmission control is what we've been talking about. It turns out that the same protocol is the standard for shipping data across the internet. An important notion is that each device along the path of our communication has to be able to read and understand the transport information. Therefore, if all the devices can read and understand the TCP/IP information embedded in our data, then all is well and all can communicate with itself. The graphic on this page is a logical representation of the Ethernet data frame, or using our analogy, Ethernet shipping package. Just as an FYI on this, the octet is 8 bits, so 2 octets is 16 bits of information. The actual data you're sending would be found in the gray box section of this graph. The rest of the information is for the intermediate devices so they can understand how to route your package. So a few more ideas about TCP/IP and our need to ship information across a computer network. Perhaps it would be good to mention that not all devices on our computer networks will be recognized as a computer. There are several types of devices that are tasked with helping our data communications along the way. We'll lump these interesting chunks of technology into a catch-all phrase called infrastructure. As we mentioned before, each device needs to have an NIC and must speak to the TCP/IP. The network community often refers to any device that can connect to and communicate across a TCP/IP network as a host. Before information can be sent from a host device, it is inserted into one or more of the TCP/IP packets. When that packet arrives at the final device, the TCP/IP information is stripped out and the pieces of the data are glued back together for use of the terminating device. TCP/IP has built-in capabilities for guaranteeing reliable end-to-end data service. This reliability is supported by all the intermediate devices along the way, and if a packet is lost or damaged, then it's resent. Also within the TCP/IP packet is support for any routers and switches that a packet might encounter along the way. One of the nice advantages of using a digitalized data in this fashion is that we can also include data encryption within the data portion of the packet. TCP/IP has also been around since the 1970s. We're currently using version 4 of the TCP/IP across most parts of the world. The new version 6 has been created, but it may be some time before all the internet devices can speak the new IP protocol. For now, the industry standard is still the older version 4. Now, one of the cool things about TCP/IP network protocol is its support for packet switching. Now, this graphic is meant to show you that the original message is packetized in Los Angeles. Each of the packets can take a different route across the US to New York City. Every red dot represents a router. When a packet shows up at the network interface, the router looks inside the packet, reads the location of the final destination. And there might be many possible paths to New York, but because of the network traffic congestion, a longer path might even be quicker. Routers can then route each package according to their understanding of the conditions of the communication lines at the time. This has the benefit of smoothing out traffic across a busy network connection, and it also provides a fault tolerance that allows the network to keep working even if part of the network fails. Because it's possible for the individual packet to arrive at the destination out of order, TCP/IP provides a sequence number for each packet that allows them to be reordered to their original sequence once they arrive at the terminal end. It turns out that when designing a computer network, it makes sense to give some computers special assignments. It's common that users of the network either want to share data or they want to share application programs. Some computer resources are specific to us as individual users, but are not useful for others. This might include managing our own screen and processing those programs that are only on our individual computer. In a business setting, it is often desirable to achieve some economies of scale by sharing resources across the network. By sharing an application, we don't have to install it and support it on everybody's individual machine. It also allows us to back up data from a single location rather than from everybody's individual machine. Security, support, and performance are just some of the reasons we are increasingly putting company applications on shared devices. Client computers are focused on the needs of one or a few people. We size client machines appropriately, and they rely on server machines that house the shared applications and data. These machines that service multiple people and shared applications are called servers. Servers tend to require more complicated computing and storage capacity given their role in serving many clients. Client-server computing links two or more computers in an arrangement in which some machines called servers provide computing services for other PCs called clients. Networks that have only one or a few computers are often organized in a simpler peer-to-peer network, where the printer or storage attached to one of the computers is available to the others on the network. This simple network doesn't need dedicated servers. It's worth mentioning another term that we hear about in the form of client-server computing, which is called cloud computing. While you hear a lot of hoopla about cloud computing, it's mostly from the vendors trying to sell services. The primary difference between client-server and cloud computing is who owns the server. In cloud computing, the servers are typically accessed through the internet and are most often owned by a third-party vendor. It's a slick way to outsource some things like data storage, access to key applications, and perhaps even lease some hardware at someone else's facility. Cloud computing has allowed even small firms to access powerful tools through a lease arrangement with service providers. There are plenty of pros and cons to outsourcing computing resources. If you have an interest, there are millions of words written on the topic. So I'll limit our discussion about the internet to this single slide. There's a lot of interesting topics that relate to the internet, but we'll leave those for a different time. I want to address how we connect our computer to networks on the internet. When your home network has only a single computer, or you work for a company that with tens of thousands of employees, you both connect to the amazing resources of the internet in roughly the same way. You gain access to the internet through an intermediate service provider, or ISP. You use a router of some type to connect to your network or your ISP, and then they use another router to connect to the broader backbone of the internet. It turns out that every single host device connected to the internet has to have a unique Internet Protocol, or IP, address. Just like a UPS package needs to have a unique address to get the package to you, every device on the internet also must have a unique address. One of the reasons the TCP version 4 protocol is becoming so outdated is that it only supported 4 billion addresses, and we simply run out of addresses. Version 6 will contain trillions of addresses when it becomes standard. As it often happens, your ISP gets a block of internet addresses that they re-release to you. The main point of the slide is to say that no matter how you get to the internet, whether fiber optics, satellite, cable modems, or DSL, all have to access the internet and go through an ISP. The primary takeaway for this chapter is the fact that all modern information systems are built on top of computer networks. When individual contributors don't have to understand the nature of networks, but their managers need to understand the potential limitations offered by today's networks. Modern business decision-making is increasingly data-driven and therefore network-driven. The goal of business managers is to make better decisions through more efficient use of information. Information systems are essentially a tool in decision-making for businesses going forward.